You say a word out loud. All that leaves your mouth is shaking air, a wave of pressure rippling outward. A microphone turns that ripple into a wiggly line, a long list of numbers. And somehow a machine reads that mess of vibration and writes down the exact words you said in your language, even with an accent, even over background noise. How? We are going to take it apart using the clearest worked example out there, a system called Whisper. But Whisper is just our specimen on the table. The real subject is the durable idea underneath it, the recipe that powers the captions on your videos, your voice assistant, your phone's dictation, and whatever replaces them next. By the end, you will know exactly how a machine turns your voice into text, where it is genuinely clever and where it quietly slips. And here is the one idea to hold on to the whole way through. The network never actually hears your voice. It looks at a picture of it. Whisper is an open-source speech recognition system from OpenAI, released in September of 2022. Software that turns spoken audio into written text and can also translate it. The technical name for that job is automatic speech recognition, or just speech-to-text. The crucial part is how it's shipped. The code and the trained weights are public, under the permissive MIT license, which allows commercial use, so anyone can download the whole thing and run it on their own laptop for $0. And inside, it connects to everything else on this channel. Whisper is a single encoder-decoder transformer. If you have heard us explain language models, that should ring a bell. Tokens, attention, an encoder, a decoder, the same machine, just sequence to sequence, a sequence in and a sequence out. Here a sequence of sound goes in and a sequence of words comes out. One careful point we will reuse. Whisper is not a large language model. It contains a text-writing piece that works just like the inside of one, but the system as a whole has an ear that reads sound. So it is a speech-to-text model, the same brain you already met, given a new sense. Now the single most important design choice. How do you teach a machine to hear? You show it an enormous pile of examples. Whisper was trained on around 680,000 hours of audio scraped from across the web, podcasts, lectures, videos, each clip paired with its existing transcript. That word paired matters. Every piece of audio came with text saying what was said. But those transcripts are messy, imperfect, full of small errors, so this is called weak supervision. And here is a misconception to kill right now. Weak does not mean the labels were missing. It is still supervised learning, audio matched with text. The weak just means the text is noisy, not hand-cleaned. The bet was that sheer scale beats careful cleaning. Roughly 2/3 is English audio to English text, about 1/5 is other languages translated into English, and the rest is other languages kept in their own script, spanning nearly 100 languages in all. So why was this a big deal? Before Whisper, good speech recognition usually meant renting it. You sent your audio up to a company's cloud server, paid a fee for every minute, and your recording left your device. Whisper changed that. Because the weights are open and free, accurate transcription became something you run on your own machine, offline, with nothing leaving your laptop and no per-minute bill. A genuine shift in access. But the deeper reason it matters is the timeless lesson it teaches, the one that outlives the product. Speech recognition is just sequence-to-sequence prediction over a picture of sound. Turn the sound into an image, let a neural network read the image, and have it write the words one piece at a time, exactly like a language model continuing a sentence. Every modern speech system rides that same skeleton. Whisper is one clear instance of it, and so is whatever you will be using in 5 years. So what can one set of these weights do? A surprising amount, all from the same model. First, it transcribes speech to text in the same language across roughly 100 languages. You speak Portuguese, you get Portuguese text in the correct alphabet. Second, it can translate speech into English, and we must be exact here. The translate task goes from any of those languages into English, and only English. It does not do arbitrary pairs, not Spanish to Japanese, just everything into English. Third, it produces timestamps, lining the words up with the audio to generate subtitles automatically. Fourth, it can identify which language is being spoken, and even tell whether anyone is speaking at all, separating speech from silence. 4 jobs, 1 network, and the way it picks between them is one of the most elegant tricks in the whole system. First, let us open the box and see how it hears. Here is the heart of it, the part to slow down for. We start with the raw signal, the waveform air pressure measured over time. Whisper resamples everything to 16,000 measurements per second, working in fixed 30-second windows. Just a long, wiggly line. The trouble is a wiggly line is hard to read, because the real information is hidden in its frequencies, the pitches stacked inside it. So Whisper performs a transformation. A tiny analysis window, about 25 milliseconds wide, slides along the wave in little 10-millisecond steps, and at each stop asks one question. How much energy is at each pitch right now? Each answer becomes a vertical stripe of color. Stack those stripes left to right and the flat line stands up into a 2-dimensional picture, a heat map called a spectrogram. Time runs across, pitch runs up, brightness is loudness. The sound has folded into an image you can actually look at. But Whisper makes 2 more adjustments, both borrowed from how human ears work. First, it warps the pitch axis onto the Mel scale. Our ears catch fine differences down low but lump together the high pitches, so the Mel scale spaces things the same way, detailed at the bottom, coarse at the top. Second, it puts loudness on a logarithmic scale, because we hear loudness logarithmically too. A whisper and a shout are not as far apart to us as the raw numbers suggest. Apply both and you get the log-Mel spectrogram, a grid of frequency rows by time slices. And now the load-bearing insight of this entire video. This picture is what the neural network actually sees, not the sound. Never the sound. The model is not listening at all. It is reading an image of your voice, the way you would read a photograph. Now a transformer reads that picture, in 2 stages that mirror the language model parts you already know. First, the encoder. The spectrogram passes through a small convolutional stem, a couple of layers that sweep little filters across the image to clean it up and pull out local features, and they also have its length in time. Then position tags are added so the model knows the order of moments. After that comes a stack of transformer encoder blocks, and inside them is the attention we have described before. Every slice of time gets to look at every other slice, near and far. Out of this, the colorful grid is distilled into a tidy row of abstract vectors, the encoder's representation. Think of it as the meaning of the sound. This shape is a hissing S, this rising contour is a question. And the encoder does this once over the whole 30 seconds before a single word is written. Now the second stage writes the text, and this is where it becomes, almost literally, a language model. The decoder generates the transcript 1 token at a time, a token being a subword piece, the same kind of chunk a language model deals in. At each step it does 2 things at once. It uses self-attention to look back at the words it has already written, keeping the sentence coherent. And it uses cross-attention to reach into the encoder's picture of the sound, to check what was actually said. Then it predicts a probability over the next token, picks 1, and repeats. That is why people call Whisper's decoder an audio-conditioned language model. It is doing next token prediction, the exact trick behind every chatbot, except each guess also gets to peek at the sound through cross-attention. A language model predicts the next word from the previous words. Whisper predicts it from the previous words plus a picture of your voice. So how does one model do 4 jobs? Here is the elegant trick. Before the decoder writes any real words, it is fed a short sequence of special control tokens that tell it which task to run, almost like a tiny prompt of switches. A start token, then a language token, then either a transcribe switch or a translate switch, then a setting for whether to include timestamps. That is the whole multitask magic. Swap transcribe for translate and the very same wait stop writing the original language and start writing English instead. No second model. Language identification is simply which language token it predicts first. Detecting silence is its own token. And those subtitle timestamps are tokens too. The time axis chopped into special markers the decoder sprinkles between the words. Captions, translation, language detection, all steered by a handful of switch tokens up front. Two honest notes on why this works so well. First, where does the accuracy come from? Not from a clever architecture, the transformer here is deliberately plain. It comes from those 680,000 hours of messy, varied, real-world audio. Train on that much diversity, and the model handles accents, noise, and topics it was never tuned for, straight out of the box. Same story we tell about language models. Scale of weak data beats careful hand tuning. Second, a decoder that writes one token at a time can misbehave. Because it is a language model at heart, it sometimes wants to keep talking, looping, or inventing. So Whisper adds guardrails when it decodes. It can use beam search to weigh several candidate transcripts and a temperature fallback. It starts cautious, and only if the output looks broken, too repetitive, or too unconfident does it rerun that chunk with more randomness to shake loose. And one bonus. Those tight word-by-word captions come from reading the cross-attention itself. Certain heads learn to point at the exact slice of audio for each word, so the timing falls out of attention, with no added stopwatch. So where does Whisper sit in the wider world? Two things are true at once. First, it is wildly popular, the de facto open baseline for speech-to-text, with a whole ecosystem built around it. Faster versions, tiny versions for a phone, versions that add speaker labels. As open speech models go, it is among the most downloaded ever. But, and this is the part that ages, by now it is no longer the most accurate. On the public leaderboards that rank these models by error rate, newer systems have edged above Whisper, including models from NVIDIA and others. Some far faster too, and OpenAI's own hosted models compete as well. So the honest, durable framing is this. Whisper is one of the most widely used open speech models, robust and multilingual, but not the accuracy champion anymore, and the rankings shift constantly. No single model wins on every axis. Some lead on raw English accuracy, some on speed, and Whisper still shines on broad multilingual coverage and translation in one open package. It changed the game. Then the game moved on, which is progress, not failure, since many of those newer models are its own descendants. So how would you use it, and what does it cost? There is a fork in the road. Down one path, you run it yourself, free. Because of that MIT license, you install Whisper on your own machine and pay nothing but your electricity, with faster community versions for everyday computers and lighter ones that run on a plain processor or even a phone. Down the other path, you call a cloud transcription service and let someone else run it, and that bills by the minute of audio, not by the token, roughly fractions of a cent per minute. Prices drift, so just remember the shape. Free if you self-host, a small per-minute fee if hosted. Whisper also comes in a size ladder, from a tiny model light enough for a phone up to a large one that wants a real GPU, trading speed for accuracy as you climb. And the uses are universal. Captions for videos, transcribing lectures and interviews and podcasts, dictation, a live accessibility aid for people who are deaf or hard of hearing, and the listening front end of a voice assistant, where Whisper hears, a language model thinks, and a text-to-speech voice replies. Now the honest limits, each a window into the mechanism, not the machine being broken. First, hallucination. Feed Whisper pure silence or non-speech noise and it can invent words that were never spoken, because the decoder is a language model that wants to keep generating, so with nothing real to transcribe it sometimes fills the void with plausible text. Related to that, it can fall into repetition loops, the same phrase echoing, which the guardrails reduce but do not perfectly cure. Second, it works unevenly across languages, a spectrum, not a verdict. The more audio a language had in training, the better the model does on it. Languages with little audio on the internet get less accurate results, a real global fairness point touching billions of speakers. There are also measurable gaps across accents and speaker groups, but notice the framing. Strong accent handling is one of Whisper's headline strengths, and the remaining gaps are about data coverage, not some inability. And finally, the base model does not natively tell you who spoke. It reasons in those 30-second windows, and the ethical line is real. Transcribing people without consent or using this for surveillance is off-limits. Let us flip the common misreadings one at a time. 1. It hears the audio. No, the single biggest takeaway here, the network never touches raw sound. It sees a log-Mel spectrogram, a picture of sound, and reads it like an image. 2. Whisper is a language model. No, it is an encoder-decoder speech-to-text model. It contains a language model-style decoder, but the system as a whole reads sound and writes text. 3. It taught itself, unsupervised. No, it learned from messy but real labels, audio paired with imperfect transcripts, supervised just noisily. 4. It can translate any language into any other. No, it translates into English and only English. 5. Whisper is the best, most accurate speech model. That is out of date. It is the most widely used open one, but newer models beat it on accuracy. And 6. AI cannot understand accents. Wrong and worth retiring for good, because accent robustness is one of Whisper's strengths, and the residual gaps are a data story, not a limitation of the idea. One more myth than the payload. Does Whisper understand your voice the way a person does? Not quite. It converts your speech into the right words with remarkable accuracy, but it does not grasp the meaning of what you said. That is the next stage, a language model that thinks about the transcript afterward. Whisper hears, something else understands. Keeping those apart keeps us honest. So step back. The real payoff is that tokens, attention, encoders, decoders, next token prediction, the toolkit behind chatbots, also powers hearing. A language model predicts the next word from the previous words. Whisper predicts it from the previous words plus a picture of the sound. One architecture, many senses, and you can already guess images and video plug into the same machine the same way. And the recipe outlives the product. Sound becomes a picture, a network reads the picture, it writes the words. That is how Whisper works, how your phone's captions work, and how whatever comes next will work too. Whisper just gave the whole field a free, open place to start. Here is the whole thing in one line. A machine never hears your voice. It looks at a picture of it and reads.